Alrighty, so cross product. So our second thing called product in its name, different than dot product. And again, it does not mean multiplication. So it's got product in the name. It's not a multiplication thing. So again, I'm going to start with the formula and then we'll see what this formula does. So I have two vectors, vector A, and we're crossing it with B. And we'll see that you get a2b3 minus a3b2, comma, a3b1 minus a1b3, comma, a1b2 minus a2b1, and all of that's in brackets. So what I want you to see is that this is written as something, comma, something, comma, something. So we are getting a vector as an answer, as opposed to a dot product. You took two vectors, you dotted them, your answer was a scalar. The formula is showing you that you are getting a different vector. When you cross two vectors, you get a different vector. These vectors are written in 3D. Cross product has to be done with 3D vectors. There's no such thing as the cross product of two 2D vectors. It's not defined for 2 space, just for 3 space. And we'll talk about why in a second. So this formula looks ridiculous. Luckily, you never have to use the formula as that. I've got a little trick that sort of sets this up correctly for you. So I'll just show you an example of how to do a cross product of two vectors. So I'm going to take the vectors 1, 2, 3, and the vector 4, 5, 6, and we're going to do A crossed with B. We're going to cross those two vectors. So my final answer will be a vector. So instead of writing out that full formula, the trick to actually calculating this cross product is you write the first vector first, and order here does matter. So we're doing A cross B, so I write A first, and I write it out 2 times like that. And then B second, and again, I'm going to write it out 2 times like that. And then what I'm going to do is cross out the first and cross out the last. So you're like, why did I write them in the first place? It's just, it'll be faster to write out the full vector than remembering to start at the second and end one short of the last. It's easier, just write it out twice. And then to do the cross product, what you do is you do this cross, sort of like Chrissy cross. You do 2 times 6 is 12, but then it's a subtraction. You subtract the other one, subtract 5 times 3, and that becomes negative 3, and that's going to be our first component of our answer. And you'll see what we did was a2 times b3, and then subtracted a3 times b2. So this is just a shortcut to sort of line things up in the right way. So you always start in the top left, do the cross, and subtract. And then you move one set over, and you're going to do this times this. So 12 minus 6. And 12 minus 6 is 6. That's our y component of our cross product vector. And for the last one, 5 times 1 is 5. Subtract 4 times 2 is 8. Negative 3. So negative 3, 6, negative 3 is our new vector. What is that vector? We're not quite sure yet, but that's the cross product of those two vectors. That's just the definition using the formula. That's what we've got. So we've got 2 types of products. So this is a cross product. And our other one is a dot product. So just for practice, what I'm going to do is I'm going to dot this new vector we got, the cross product vector, with the first vector, just to practice our dot product. I don't have any hidden meaning behind this at all. That would be crazy. And remember, we do x times x, so 1 times negative 3, plus y times y, so 6 times 2, plus 3 times negative 3, so that'll be negative 9. And I get, let's see, negative 3 plus 12 is 9, take away 9. Oh, I get 0. That's weird. Oh, I'm just practicing dot product here. So I'm going to take the other vector that we started with and dot it with that answer that we got. X times x is negative 12, y times y is 30, and then z times z is negative 18. Adding those things up, negative 12 and 30 is 18, subtract 18 is, 0. Oh, that's weird. And then I think back to dot product lesson, and if a dot product was 0, it meant the angle between the vectors was 90 degrees. And so this new vector, this cross product vector, is perpendicular to A, and it's also perpendicular to B. It's perpendicular to both our starting vectors. And that's not a coincidence. That's what cross product is meant for. Cross product gives you a new vector that is perpendicular, and the fancy math word for that is we're going to say normal to. So if two vectors are normal, it means they're perpendicular. So I'll write perpendicular in brackets because I want us to get used to using normal first. Perpendicular to both starting vectors. Okay, so that's its purpose. So what the picture looks like is you have, so again, we're in 3D. You have, say, a vector A. You have, say, a vector B. Any two vectors will lie on the same plane. There will be a flat surface, doesn't matter how angled they are in space. There'll be some flat surface that you can draw to connect those two vectors together. And then the cross product vector is perpendicular to both of those. So it's coming straight out of that plane, perpendicular to both. So you can take, your two fingers and point them in two different directions, and then imagine the plane, so maybe a webbing connecting your two fingers, connecting them together, and then the cross product would be sticking 90 degrees out of that webbing that's connecting your two fingers. I'll show you in class because that's hard to describe on this video and I don't have a camera to show myself. But that's the idea here. So you get a new vector that's perpendicular to both of the starting vectors. And here order matters. It's not a commutative operation. If you switch the A's and B's around, you actually, right, if I put 4, 5, 6 first and 1, 2, 3 second, I'd get all the same things, but the subtraction would be in the other order. So you actually end up with the negative of what you would get if you did it in the wrong order. So A cross B would be going that way, maybe B cross A would be going that way. Straight down instead of straight up, but still 90 degrees to both. So they'd be opposite vectors, same length. It is distributive, so if you're doing A crossed with B plus C, you can distribute the sort of cross product through and get A cross B plus A cross C. And then our third property is if you have a constant times a vector, times the cross product, you can multiply that constant by one of the starting vectors before doing the cross product, and you'll get the same overall resulting vector. The scalar multiplication can kind of be done in any order, I guess is a way to phrase that third property. So it gives some vector perpendicular to both. So it's perpendicular to both. The magnitude of that vector, so how long it is sticking out of the plane, is always works out to the magnitude of A times the magnitude of B times the sine of the angle between these two vectors. So that's always the that's how long the vector is, and then which way it sticks out, either up or down. There's something called the right-hand rule or something like that that would show the direction. I'm never going to worry too much about the direction for our course, but if you get into like a physics course, you might have to learn a left-hand rule or a right-hand rule depending on how they teach it, but that shows you whether it's going to be sticking up or sticking down, but we're not really worried about that for our course. We'll probably never actually use this formula. I just want you to see it. And then never use this to find theta. So like we could do with the dot product yesterday, we could get the dot product between the two vectors one way and then get their magnitudes the other way and then solve for the cos theta in that formula and solve for the angle. That works great with the dot product formula. It'll never work quite right with this one because this is always positive, so you kind of lose the sign there. So when you solve for theta, it'll always give you an acute angle. So what works out to, if the angle was supposed to be 120, you'd solve it and you'd think it's 60 if you use this formula. It would always be off by the 180 minus sort of thing. So you just never do that. Always use dot product to get the angle, never cross product. And dot product's way faster than cross product anyway, so I don't know why you would want to, but I've seen people try it on a test and get the wrong answer for the angle. So don't use that to find angles, but that is what it is. Specifically, why is it that length? Well, I think in physics, rotational forces is called a torque, and your torque is the force vector. Sorry, your torque vector, I guess it would be, is your force vector multiplied by your radius vector, or sorry, not multiplied, crossed with your radius vector. So how much force you put in a rotation would be the magnitude of that force would play into it. Also the magnitude of the radius, so it's a rotational force, so I'll give you some examples. Times the sine of the angle between them, that would be how much force you're applying. So if you picture pushing on a door to rotate the door open, how hard you push shows how quickly the door, or how much force you push to make the door move. The radius that you're pushing at also changes that. So try and push the door open with your hand right at the hinges. It's very hard to move the door versus putting your hand at the outside where the handle normally is. If you push on that, increasing the radius increases your rotational force and makes that door rotate open. And then the sine of the angle between your force and the radius. So if you're pushing it at 90 degrees to the door, that's going to be the best way, because that'll make sine theta 1, and that's the max that sine theta could be. But if you're pushing at a weird angle on the door, it won't open as easily as if you push straight on, is kind of what's happening there. The other thing is, like, another good application of torque and seeing this, if you're trying to get like a rusty bolt loosened off, a rusty bolt and nut loosened off, the longer the wrench, the longer the radius, the more rotational force you get on that nut. So you'll see if somebody's got a stubborn bolt that won't loosen, using the longer wrench makes it work a lot easier than using a shorter wrench. So you'll see that come up all the time if you've worked with that sort of stuff before. But that's, a physical application of cross product. We're going to be looking at the math applications of it. So basically, you need to know how to calculate it using that shortcut. You need to know that it gets a vector that's perpendicular to both starting vectors. Those are the key things. So with these examples, we're going to now find a unit vector perpendicular to both of these starting vectors. Okay, so the way this is going to work, how we're going to use cross product, is cross product gives you some vector that's perpendicular to both. So we'll get the cross product first, and then we'll kind of make it the right size, make it a length of 1 after the fact. So I'm going to go off to the side and write out A first, write out B second, twice each, cross out the end, and then I'll write a space for my answer over here. A cross B is, and we just got to be really careful with the negatives involved in this one now, so this is where it gets a bit tricky. So negative 32 subtract negative 14, so really adding 14. So that's going to be, what's that, negative 18. Next one is 10 subtract positive 24, because the two negatives there, so that'll be negative 14. And then the last one, positive 21 subtract positive 20, so 1 there. And so that's what I got for the cross product. I'm going to be I always take a moment and just pull out my calculator and do a quick dot product. So I'm going to do just with maybe the first one there, negative 18 times negative 3 plus 4 times 14 plus 2 times 1. And I did not get 0 there, so I have messed up somewhere along the lines here. So let's just double check our work. Oh, I do get 0. I typed in the dot product wrong. So that was my mess up. So that is the right cross product, it looks like. So I normally just double check with one of the two vectors. If one of them comes out 0, it usually means that the cross product you've done correctly, because if you've messed up a minus sign, then it's going to mess up both and neither is going to be 0. If you want to be extra careful, you can double check with the second vector, but I think that's a bit overkill. So I did a quick check, and negative 18 times negative 3 plus 4 times negative 14 plus 2 times 1 is in fact 0. So that is perpendicular to A. I bet B is going to be perpendicular as well, because that's how cross product works. And then from there, now we want to make it, that's got the right direction, it's got the wrong length. Obviously that vector is longer than 1. So what we're going to do is make our unit vector. So I'll just call it U. And what we're going to do is take this vector and shrink it down by its size. So we're going to divide it by its size, or really we're multiplying by 1 over its size. And its size is going to be the square root of 18 squared plus 14 squared plus 1 squared. Again, don't have to worry about the negatives there. Which is the root of 521. So I can write this as negative 18 over root 521, negative 14 over root 521, and 1 over root 521 would be a vector that is 1 long and perpendicular to both. So that's going to hit both things. So here's the other flavor of this question, is I've told you that x 21 and z is perpendicular to both a and b. So it is parallel to this cross product vector. It is on the same direction or the complete opposite direction of that cross product vector, which means if two vectors are in the same direction or collinear or parallel, however you want to say that, it means one is a scalar multiple of the other. So x21z would have to be some scalar multiple times that cross product that we've already found. So something like that. So if we focus in just on the y's, we see 21 has to be negative 14 times k. So divide by negative 14, divide by negative 14, and we'll get k is 3 over 2 if we reduce that, and negative, obviously. So that's our k value, so I'm going to use that to, so x would then be negative 18 times negative 3 over 2, which is 27, I believe. And y would be 1 times negative 3 over 2, so k times, sorry, not y, that's the z. So just negative 3 over 2 for z. And we have that. Okay, so those are our examples. So on the formula sheet, you should add on the full long formula, but also sort of this demonstration of how to get there. And then you can put down that magnitude formula, but again, I think I've cut out everything where we would ever actually have to use that. But might as well have it on your formula sheet. Note that you probably won't use it, and you definitely shouldn't use it to find the angle because it gets messed up. And then just some notes to yourself. Remind yourself how to calculate the cross product and describe what this new vector is, what's special about this new vector. And then, well, I guess I never said why you can't do cross product in 2 space. Well, if you have 2 vectors in 2D, there isn't going to be a third. If I'm not allowed to leave the page, I can't make a third vector that's going to be perpendicular to both. I can make one that's perpendicular to that one, but in general, unless you start it with 2 parallel vectors, not going to work. So there's no one vector that's definitely going to be perpendicular to both unless you're allowed to stick out of the page in the third dimension. So that's why you can't do that in 2-space. And then the practice we'll handle in class.